Graphics programming. It is a skill which people use to digitally edit visual data and present it to users. In order to draw anything on the screen, you need an API to communicate with the graphics processor, such as OpenGL. First, we need some data to draw. GPUs usually draw triangles because of their simple nature. You can make anything out of them. They are formed with 3 vertices that hold the position and UV coordinates of each point, and together they form meshes. UV coordinates are used to know which part of a texture to apply to each pixel later down the line. Meshes are objects that our scene consists of, and they can be both 2D or 3D. When we have the triangle data we want to draw, we might want to transform it, which is where Vertex shaders come in. But wait, what's a shader? Well, simply put, it's a program that's running on the graphics processing unit, GPU for short, and is highly parallelizable, which means it uses many of the GPU's cores to process lots of data simultaneously, which is great for dealing with lots of small tasks. The vertex shader specifically is used to manipulate the vertex data of our meshes, such as the vertex position or the UV coordinates, which are later used for sampling a texture. We can translate, rotate, scale, or perform any other imaginable operation on the points constructing our mesh. This is how our mesh data looks like on the screen. All we have on screen right now are the triangles we defined. The GPU still has to rasterize the mesh data in order to render any sort of texture. After the mesh is rasterized, aka the pixels of the surface are constructed, a fragment shader is applied. It runs for every pixel in our surface. In the fragment shader, we can apply a texture by sampling it and setting it to the final color of our pixel. After rasterization and texturing, our scene looks a little like this. But that's not it. With shaders, we can do a lot more. But how did we make all of that? As I mentioned before, shaders run in unison and can perform thousands of simple calculations at the same time, which makes them very powerful for manipulating graphics data in all sorts of ways. Furthermore, we can send values from the CPU to the GPU. Those are called uniforms. We should do so sparingly, as transferring data from the CPU can easily become a bottleneck. For example, when sending big textures back and forth. Uniforms are awesome because we can tell the shader to use many different values that depend on things in other parts of our program, such as time or even full-on game mechanics like wind speed or the sanity stat in the hit survival roguelike Don't Starve by Clay Entertainment. We can also send pre-rendered images for many cool effects. Most commonly for VFX artists, this is some kind of noise, be it smooth or a bit wilder, but you can send any image and make the shader do anything to the vertex or color data with it. This is why shaders are very powerful. You can present data from the CPU and do whatever you want with it, because a shader is a program like any other, with only minor limitations. The only real limit is our creativity. Let's say you wanted to, for example, have a picture of a dog, then offset the sample by a noise texture, but also offset the sample of the noise texture by time and then hook this effect up on a sine wave. You can. Stylized rendering is often utilized today to cut on production costs and let VFX artists express themselves in a creative way. This is a very useful tool and is why many indie games today are able to look the way they do. Graphics programming is very interesting and fun because of the many possible outcomes of your programs. I hope you like learning about shaders, but make sure not to overuse them because they can often lower visual clarity and make it not fit the art direction. and most of the time a CPU program is the preferred solution.